late 2019, astronomers watched a star begin to disappear. Not a distant anonymous speck of light, but Betelgeuse, the red beacon marking Orion's shoulder, visible from nearly every inhabited region of Earth. A star so immense that if it replaced our Sun, it would engulf Mercury, Venus, Earth, and Mars. A star whose light began its journey toward us in the 14th century, when medieval empires dominated the world, and is only now arriving. For more than 100 years, Betelgeuse behaved exactly as theory predicted. It pulsed every 400 days in a slow, measurable expansion and contraction. Its radius, between 700 and 900 times that of the Sun, aligned with stellar evolution models. Deep inside, helium fused into carbon and oxygen. Advanced in age, certainly, but stable. Then, in September 2019, its brightness began to fall. At first, the change seemed routine. Red supergiants are variable by nature. But by December, observatories across the globe were reporting something unprecedented. The dimming was accelerating beyond historical patterns. On February 7, 2020, Betelgeuse reached magnitude 1.614, the faintest level recorded in more than 150 years of systematic measurement. It had lost over two-thirds of its visible light. This was not a subtle fluctuation detectable only by sensitive instruments. Anyone who knew the winter sky could see Orion's shoulder fading. The response from the scientific community was immediate. NASA's Hubble Space Telescope detected ultraviolet signatures of superheated plasma blasting away from the star at more than 200,000 miles per hour. The European Southern Observatory's Very Large Telescope captured images showing one hemisphere nearly 10 times darker than the other. Teams at the Harvard-Smithsonian Center for Astrophysics concluded that Betelgeuse had expelled an enormous bubble of material, a surface eruption powerful enough to eject between 0.02 and 0.08 times the mass of Earth in just months. The gas cooled as it expanded, condensed into microscopic dust grains, and drifted across our line of sight, partially obscuring the star. The explanation was elegant. Multi-wavelength evidence converged. The dimming was not the prelude to an explosion. It was a massive stellar outburst, dramatic but survivable. By the spring of 2020, the dust dispersed. Betelgeuse brightened again. The crisis appeared resolved. But something deeper had shifted. The familiar 400-day heartbeat, a rhythm tracked for generations, did not return. Instead, the star began pulsing twice as fast. The surface had recovered, the light had returned, yet the internal rhythm was different. It was as if the eruption had not merely dimmed the star, but reached into its interior and altered the way it breathes. And that change would force astronomers to confront a far more unsettling possibility. The star they thought they understood may never have been as stable as it seemed. When the light came back, the real mystery began. By April 2020, Betelgeuse had largely recovered its brightness. The dust cloud that dimmed it had dispersed into space. Headlines faded. The immediate crisis appeared resolved. But as astronomers continued their measurements, something far more profound emerged. The star's pulse was no longer the same. For over a century, Betelgeuse had followed a dependable 400-day cycle. This rhythm represented what physicists call the fundamental mode of pulsation, the entire star expanding and contracting together like a single breathing sphere of plasma. The timing matched theoretical predictions for a red supergiant with a radius between 700 and 900 times that of the Sun. After the Great Dimming, that 400-day cycle vanished. In its place was a new oscillation, approximately 200 days. The star was breathing twice as fast. This was not a minor fluctuation, it was a structural shift. Observatories monitoring Betelgeuse through 2020 and 2021, including data analyzed by astrophysicists at the Harvard-Smithsonian Center for Astrophysics, confirmed the persistence of the shorter period. The eruption, it seemed, had done more than eject material. It had disrupted the internal equilibrium of the star. The leading explanation involved shock waves. When the massive convection bubble burst through the surface in late 2019, it likely generated powerful pressure waves that traveled back into the stellar envelope. Instead of the entire star moving in synchrony, the outer layers began oscillating out of phase with the interior. This configuration is known as a first overtone mode, a higher frequency vibration that normally requires additional energy to sustain. In stellar physics, overtone modes are expected to damp out. Models predicted that within 5 to 10 years, the fundamental 400-day rhythm would reassert itself, but as of 2024, it has not. The shorter period remains dominant. This persistence raises uncomfortable questions. Either the damping timescales in red supergiants are poorly understood, or some external mechanism is continually injecting energy into the star's envelope. The stability once attributed to Betelgeuse now appears conditional, fragile. The stakes extend beyond a single star. Pulsation periods are directly linked to stellar structure. If our interpretation of these oscillations is incomplete, then our estimates of mass, radius, and evolutionary stage may also require revision. A star that served as a benchmark for late-stage stellar evolution had abruptly shifted behavior in ways theory did not anticipate. And, as astronomers examined the data more closely, another pattern, a slower, longer variability cycle that had lingered unexplained for decades, began to demand attention. The deeper they looked, the more it seemed that the dimming was not the anomaly. It was the warning. Long before the Great Dimming, Betelgeuse was already whispering a second rhythm. For decades, astronomers had recorded a slower, puzzling variation in its brightness, a cycle lasting roughly 2,100 days, nearly 6 years. It did not match the 400-day fundamental pulsation. It did not align with known overtone behavior. The signal was persistent, measurable, and unexplained. At first, the anomaly was treated as background complexity. Red supergiants are turbulent. Their enormous convection cells can rise and fall over years. Some researchers proposed that rotating surface features were moving in and out of view. Others suggested exotic pulsation modes not yet fully understood. But none of the models fit cleanly. By 2023, as the 200-day pulsation persisted and Betelgeuse brightened beyond historical norms, attention returned to that 6-year cycle. If the star's interior had truly shifted, perhaps this longer variability held the key. In December 2024, a team led by Dr. Steve Howell at NASA's Ames Research Center decided to test a more radical hypothesis, that the signal was not internal at all. They turned to the Gemini North Telescope in Hawaii and deployed a specialized instrument known as Alopeci, a high-speed speckle imager capable of overcoming atmospheric distortion by stacking hundreds of rapid exposures. The goal was simple in concept, but technically formidable. Look for something hidden in the glare of Betelgeuse. What they found was extraordinary. Just 52 milliseconds from the red supergiant, an angular separation equivalent to seeing a coin from thousands of kilometers away, a faint point of light appeared. Betelgeuse was not alone. The object, later confirmed through follow-up analysis and announced in mid-2025, was a companion star approximately 1.5 times the mass of our Sun. It orbits at roughly 4 astronomical units, about the distance between Mars and Jupiter. But here is the critical detail. Betelgeuse is so vast that its extended atmosphere stretches outward beyond that distance. The companion is not circling outside the star. It is moving through the outer layers of the star's own envelope. Spectroscopic studies, including multi-year data analyzed by teams at the Harvard-Smithsonian Center for Astrophysics, revealed periodic disturbances in the motion of gas surrounding Betelgeuse. The timing matched the 2,100-day cycle with striking consistency. The unexplained signal was not a mysterious pulsation, it was a wake. As the smaller star plows through Betelgeuse's atmosphere at roughly 6 kilometers per second, it compresses gas ahead of it and leaves behind a dense, expanding trail. When that wake drifts across our line of sight, it partially absorbs and scatters light. The 6-year rhythm was orbital. The implications were immediate. If a companion star is embedded within the atmosphere of a red supergiant, then mass loss, pulsation behavior, and even the star's long-term evolution may be influenced by binary interaction. Betelgeuse was no longer a single aging giant approaching the end of its life in isolation. It was part of a dynamic, interacting system. And if one companion had remained hidden for decades, a deeper question began to surface. How much of this star's behavior is truly its own, and how much is the result of gravitational forces we are only now beginning to see? What happens when a star does not die alone, but is stirred, shaped, and possibly destabilized by another star moving inside it? By mid-2025, the discovery of Betelgeuse's embedded companion had shifted the entire conversation. What began as an explanation for a 6-year brightness cycle was quickly becoming something far more consequential. The companion was not a distant binary partner. It was orbiting within the extended atmosphere of a red supergiant, a configuration rarely observed and never studied in this level of detail. In January 2025, a study led by Dr. Andrea Dupree at the Harvard-Smithsonian Center for Astrophysics analyzed nearly 8 years of spectroscopic data from the Hubble Space Telescope and ground-based observatories. The findings were precise. Gas velocities in Betelgeuse's outer atmosphere were periodically distorted in a pattern synchronized with the companion's 2,100-day orbit. The smaller star was not merely present, it was actively reshaping the envelope of a star nearly 1 billion times the volume of the Sun. As the companion moves at roughly 6 kilometers per second through the extended atmosphere, it compresses stellar material ahead of it and leaves behind a widening wake. This wake is dense, turbulent, and capable of altering how energy flows through the outer layers. In a star where pulsation depends on delicate pressure balances, even subtle structural disturbances matter. This raised a new possibility. Could the persistent 200-day pulsation, the faster rhythm that emerged after the Great Dimming, be sustained by repeated gravitational perturbations? Each orbit injects mechanical energy into the envelope. Each passage generates shock fronts and density variations. In a system already destabilized by a massive surface ejection, this added forcing could prevent the star from returning to its previous equilibrium. If that interpretation is correct, Betelgeuse is no longer evolving in isolation. Its late-stage stellar physics are being influenced in real time by binary interaction. The stakes extend well beyond one star. Most massive stars are born in multiple systems. If embedded companions can significantly modify mass loss, rotation, and pulsation, then existing models of red supergiant evolution may underestimate how frequently binary dynamics shape a star's final structure before collapse. And there is another consequence. Orbital drag inside a dense stellar atmosphere extracts energy. Over time, it shrinks the orbit. Some calculations suggest the companion could spiral inward within 10,000 years, perhaps sooner on cosmic timescales, raising the possibility of a future merger. A merger inside a star already approaching the end of its life would not be a quiet event, it would be transformative. And it forces a deeper question. If Betelgeuse is being reshaped today by gravitational interaction, then what else in its past or future might still be hidden beneath its turbulent surface? What if Betelgeuse has done this before? By 2025, astronomers were no longer asking only how the companion affects the present. A more unsettling question began to surface. Is Betelgeuse itself the product of a past stellar collision? The clue lies in motion. Observations using the Atacama Large Millimeter/Submillimeter Array, ALMA, indicated that Betelgeuse appears to rotate at roughly 5 kilometers per second. For an isolated red supergiant of its size, theory predicts a much slower spin. As massive stars expand, conservation of angular momentum should dramatically reduce their surface rotation. Yet Betelgeuse spins at nearly twice the expected rate. In 2023 and 2024, computational models led by astrophysicist Sagiv Scheiber explored what would happen if a red supergiant engulfed a smaller companion earlier in its evolution. The simulations were three-dimensional and detailed, tracking angular momentum transfer, envelope mixing, and post-merger structure. The results were striking. A merged star would rotate faster. It would also display enhanced nitrogen at its surface, a signature of deep internal material, being dredged upward during the violent mixing process. Betelgeuse shows exactly that. Spectroscopic measurements reveal nitrogen enrichment beyond what standard single-star evolution models predict. The merger hypothesis explains both anomalies in one framework: increased rotation and altered surface composition. If correct, this would mean Betelgeuse is not merely interacting with a companion today, It may have consumed one in its past. But science advances through skepticism. In 2024, a team at the Max Planck Institute for Astrophysics, led by Jingze Ma, challenged the rotational interpretation. Their simulations demonstrated that enormous convection cells, some spanning a significant fraction of the stellar surface, can mimic rotational signatures in radio observations. What appears to be spin may instead be turbulent plasma rising and sinking at different velocities. The nitrogen anomaly could also arise from internal mixing processes not yet fully modelled. The evidence is suggestive, not conclusive. If Betelgeuse is a merger remnant, then its evolutionary clock may not match standard timelines. Its internal structure may be layered differently. Its mass loss history may already be more complex than assumed. And if it once belonged to a triple system, the current companion may be the surviving witness of a far more chaotic past. This possibility carries profound implications. A star formed through merger does not die in the same way as a solitary giant. Its core mass, rotation rate, and envelope structure influence the type of supernova it will produce, and whether it leaves behind a neutron star or collapses into a black hole. The question is no longer simply when Betelgeuse will explode. It is what kind of star, in truth, it has always been. And to answer that, astronomers must look deeper, not at the surface, but into the nuclear engine at its core. XXX. In June 2023, a paper quietly unsettled the astronomical community. A team led by astrophysicist Hideyuki Sayo published models suggesting that Betelgeuse might not be in a stable helium-burning phase as long assumed, but instead nearing the end of carbon burning, one of the final stages before core collapse. If correct, the implication was staggering. Carbon burning in massive stars lasts only a few thousand years. Compared to the millions of years spent fusing hydrogen or helium, it is a fleeting moment. And near the end of carbon fusion, instability grows rapidly. Once silicon burning begins, collapse can follow in days. Sayo's team examined Betelgeuse's multiple pulsation periods, the 200-day oscillation, shorter secondary variations, and the longer 2,100-day cycle, then still under debate. Their models indicated that the combination of observed periods could align with a star whose carbon fuel was nearly exhausted. The public interpretation was immediate. Could Betelgeuse explode within centuries? Perhaps even within our lifetimes? But scientific scrutiny followed just as quickly. Morgan McLeod and other researchers at the Harvard-Smithsonian Center for Astrophysics pointed out a critical inconsistency. For the carbon-burning interpretation to hold, Betelgeuse would need a radius exceeding 1,200 times that of the Sun. Direct measurements in visible wavelengths place its radius between 700 and 900 solar radii. That discrepancy is not trivial. It is structural. Further, the 2,100-day signal, once attributed to pulsation, is now understood as orbital modulation caused by the embedded companion. Removing that signal weakens the carbon-burning argument substantially. Current consensus, as of 2024, favors a helium-burning core, a stage that can persist for tens of thousands of years before advancing to the final nuclear phases. Yet uncertainty remains. Massive stars are layered engines. Inside Betelgeuse, nuclear shells fuse different elements simultaneously. Convection transports energy across vast distances. Turbulence, rotation, and binary interaction complicate the picture. Our models are sophisticated, but they are approximations. There is precedent for surprise. In 2023, a red supergiant in another galaxy exploded as supernova SN2023IXF without clear warning signs. Pre-explosion images showed a star that appeared unremarkable until it was not. Betelgeuse is far closer. At approximately 650 light-years away, it is near enough that a core collapse event would be detectable not just in light, but in neutrinos, particles released during collapse that escape ours before photons do. Detectors such as Super Kamiokande in Japan and IceCube at the South Pole stand ready. If the core falls, they would see the first signal. For now, most models indicate Betelgeuse likely has tens of thousands of years remaining, but the margin between certainty and surprise has narrowed. Because if our interpretation of its internal stage is even slightly off, if merger history or binary interaction altered its core evolution, then the timeline shifts. And that leads to the next question. If the explosion did come sooner than expected, what would it mean, not just for astronomy, but for Earth itself? If Betelgeuse were to explode tonight, the first sign would not be light. It would be a flood of neutrinos. Within the core of a massive star, gravity and nuclear fusion exist in a delicate balance. When fusion can no longer produce enough outward pressure, gravity wins. The core collapses in less than a second, crushing matter to nuclear densities. Protons and electrons merge into neutrons. Temperatures surge into the billions of degrees. In that instant, nearly 99% of the energy released escapes as neutrinos. In 1987, detectors recorded a handful of neutrinos from a supernova in a neighboring galaxy, SN 1987A. That event occurred 168,000 light-years away. Betelgeuse is only about 650 light-years distant. If it collapses, modern observatories such as Super Kamiokande in Japan and IceCube in Antarctica would detect not dozens, but potentially millions of neutrinos within seconds. The signal would precede visible light by several hours. That early burst would confirm, beyond doubt, that the core had fallen. Then the shock wave would reach the surface. As it breaks out of the stellar envelope, Betelgeuse would brighten suddenly, possibly rivaling Sirius within minutes. Over the following days, the expanding debris would grow more luminous as radioactive isotopes formed in the explosion begin to decay. Astronomers classify such events as Type II P supernovae. The P stands for plateau, a phase lasting weeks to months, during which the brightness remains relatively constant as hydrogen-rich outer layers radiate energy. Estimates suggest Betelgeuse could reach an apparent magnitude between -8 and -12 at peak. For comparison, the full moon shines at magnitude -12.6, a single point of light nearly as bright as the moon. Visible in daylight, casting shadows at night. The stakes are not catastrophic for Earth. At 650 light-years, the radiation would not strip our atmosphere or trigger mass extinctions. The danger threshold for biological harm is estimated at roughly 160 light-years. Betelgeuse lies well beyond that limit, but the scientific stakes would be immense. For the first time in modern history, astronomers would observe a nearby supernova across the entire electromagnetic spectrum, from radio waves to gamma rays, while simultaneously recording neutrinos and gravitational waves. Every stage of collapse, shock propagation, and element formation could be studied in unprecedented detail. Heavy elements, silicon, calcium, iron, and those beyond iron formed through rapid neutron capture, would be forged and expelled into space. The explosion would seed the interstellar medium with the raw materials for future stars and planets. Yet one outcome would remain uncertain. Would the collapsing core stabilize as a neutron star, a city-sized sphere of nuclear matter, or continue inward to form a black hole? That answer depends on the final core mass, shaped by millions of years of evolution and possibly by binary interaction, which brings us back to the present. Because understanding what Betelgeuse will become requires knowing exactly what it is and how its complex history has shaped its future. Betelgeuse may not be the exception. In the years following its great dimming and the discovery of its embedded companion, astronomers began asking a larger question. How many other massive stars are evolving under similar hidden influences? For decades, stellar evolution models treated red supergiants largely as isolated systems. Their pulsations, mass loss, and final collapse were calculated, assuming a single star shedding material into space. But large surveys over the past 20 years have revealed a different reality. More than 70% of massive stars are born in binary or multiple systems. In 2022 and 2023, observational campaigns using instruments such as the Very Large Telescope and ALMA expanded high-resolution monitoring of nearby red supergiants. Subtle asymmetries in circumstellar gas, irregular mass ejections, and unexplained long-period variability began appearing in more objects than expected. None were as close or as detailed as Betelgeuse, but the pattern was emerging. Binary interaction may not be rare in late-stage massive stars. It may be common, simply difficult to detect. The discovery of Betelgeuse's companion in 2024 provided a concrete example of how easily such systems can hide in glare. A star moving within an extended atmosphere does not announce itself clearly. Its gravitational influence appears only as distorted gas velocities and periodic dimming events. Without precise instruments and years of data, it remains invisible. If binary interaction enhances episodic mass loss, alters surface composition, and sustains overtone pulsations, then current stellar evolution models may systematically underestimate how chaotic the final stages of massive stars truly are. That has consequences beyond theory. Supernova brightness, explosion symmetry, and remnant type all depend on the progenitor's internal structure. If that structure is shaped by unseen companions, then interpreting distant supernova, used to measure cosmic expansion and galactic chemistry, becomes more complex. In 2023, the unexpected explosion of a red supergiant in another galaxy, SN202 3IXF, reminded astronomers that even well-studied stars can surprise us. Pre-explosion data suggested normal variability. Then, without warning, collapse. Betelgeuse is now the closest laboratory for understanding these uncertainties. It is close enough to resolve surface convection cells, close enough to track atmospheric wakes, close enough that if it collapses, neutrino detectors will provide early warning. What we learn here may recalibrate how we interpret every massive star across the Milky Way. The question is no longer simply whether Betelgeuse is unusual. The question is whether it is revealing a universal stage of stellar death we have only just begun to recognize. And if that is true, then the final act of massive stars, including our closest red supergiant, may be far less predictable than we once believed. The true significance of Betelgeuse is not how it will die, but what its death will create. Deep inside massive stars, nuclear fusion builds the architecture of the universe. For millions of years, Betelgeuse has acted as a cosmic furnace, transforming hydrogen into helium, helium into carbon and oxygen, and progressively heavier elements in layered shells surrounding its core. This structure resembles an onion. At the center, carbon and oxygen accumulate from helium fusion. Surrounding layers may burn helium, hydrogen, and eventually heavier elements as the star advances through its final stages. Each fusion phase burns faster than the one before it. Hydrogen lasts millions of years. Carbon may last only thousands. Silicon burning, the final step before collapse, can endure mere days. When collapse finally occurs, conditions become extreme beyond laboratory replication. Temperatures soar into billions of degrees. In those seconds, a process known as rapid neutron capture, the R process, forges elements heavier than iron: gold, platinum, uranium. In 2024, astrophysical models refined by international collaborations studying neutron capture physics confirmed that core collapse supernovae remain primary sites for producing roughly half of the universe's heavy elements beyond iron. The rest likely arise from neutron star mergers. Betelgeuse represents one of the nearest future contributors to this galactic enrichment. A single explosion could eject millions of Earth masses of heavy elements into interstellar space. That material will not vanish. It will mix into molecular clouds, it will condense into new stars, it will assemble into rocky planets, the calcium in human bones, the iron in blood, the silicon in Earth's crust. All were forged in stars that died long before our Sun formed 4.6 billion years ago. Betelgeuse is part of that ongoing chain. Understanding its mass loss, its rotation, its binary interaction, and its true evolutionary stage is not merely about predicting spectacle. It determines how much mass will remain in its core, whether the remnant becomes a neutron star or a black hole, how asymmetric the explosion may be, how efficiently heavy elements disperse into surrounding space. In 2023 and 2024, increasingly detailed simulations incorporated binary interaction into supernova models, revealing that companions can shape ejecta geometry and influence element mixing. If Betelgeuse's envelope has been sculpted by its embedded partner, then its future debris field may not expand symmetrically. The consequences extend across cosmic time. Every supernova alters the chemical evolution of the Milky Way. Over billions of years, repeated cycles of stellar birth and death transform a universe once composed almost entirely of hydrogen and helium into one capable of complex chemistry and life. Betelgeuse is not simply nearing an endpoint, it is approaching a transition, a transformation from luminous giant into dispersing cloud, from star into raw material. And that realization forces a final reflection. Because if massive stars are engines of creation as much as destruction, then the mystery surrounding Betelgeuse is not only about instability, it is about connection. There is a quiet realization spreading through astronomy. Betelgeuse did not simply dim. It did not merely change its rhythm. It forced us to confront how little we truly understand about the final centuries of a massive star's life. By 2025, after years of continuous monitoring, spectroscopic analysis, high-resolution imaging, and theoretical revision, the scientific community reached an unexpected conclusion. The mystery of Betelgeuse is not a single anomaly. It is a convergence of processes, pulsation instability, episodic mass ejection, binary interaction, possible merger history, all unfolding simultaneously inside one star. The central discovery is not that Betelgeuse is about to explode. It is that late-stage stellar evolution is more dynamic, more sensitive, and more interconnected than our simplified models once assumed. The Great Dimming of 2019 revealed how rapidly a red supergiant can eject planetary-scale mass. The 200-day overtone demonstrated that internal structures can be disrupted and remain altered. The 2024 detection of an embedded companion confirmed that gravitational interaction can sculpt a star from within its own atmosphere. Each event alone would have been noteworthy. Together, they redefine the narrative. For more than a century, red supergiants were treated as predictable endpoints, enormous, luminous, but fundamentally stable until the final collapse. Betelgeuse has shown that the path to supernova may involve structural shifts, hidden companions, turbulent convection, and feedback mechanisms we are only beginning to model accurately. The stakes are cosmic. Every massive star in the Milky Way will follow a similar arc. If binary interaction and episodic instability are common, then our interpretation of supernova progenitors, remnant formation, and galactic chemical enrichment must adapt. Betelgeuse is 650 light-years away, close enough to resolve its surface, close enough that its neutrino burst would reach detectors before its light, close enough that its eventual explosion will be witnessed in extraordinary detail. But it is also far enough to remind us of perspective. The light we see tonight began its journey in the 14th century. Whatever transformation is occurring there has already happened. We are observers of history written in photons, and yet in real time we are refining the equations that describe how stars live and die. The deeper lesson is not about fear of an imminent supernova, it is about scientific humility. The universe does not follow our simplified diagrams. It evolves through complexity, through interaction, through processes that resist reduction. Betelgeuse remains in the sky, pulsing in its altered rhythm, orbiting with its embedded companion, shedding material into space. One day, perhaps tens of thousands of years from now, its core will collapse. Neutrinos will surge outward, light will follow, heavy elements will scatter into the galaxy, and somewhere in that expanding debris will be the atoms of future worlds. For now, the star continues its unstable dance, not as a symbol of imminent catastrophe, but as a reminder that even the most studied objects in the cosmos can still surprise us, and that understanding the universe is not a finished task, but an unfolding journey.